Good morning, one and all. So we are going to see the experiment number 5 today, and here we are going to see the RLC response, RLC second order circuit response for different damping conditions. So write down this as a title of the experiment, that is second order RLC response, second order RLC step response for different damping conditions. So write down this topic I am giving in the chat box. So this is second order RLC, second order RLC step response for different damping conditions. So I have given the title in the chat box. Everybody please copy it. This is going to be the 5th experiment and the most important experiment as far as this lab is concerned. So out of 10 experiments, whatever we are going to do, this thing is going to be most important. And we used to find very good response from students in this experiment while we used to do that in lab. Today it will be a little difficult, but anyways, I'll try my best. So you also be with me to understand every part of this experiment. So first let us do the build up. Yesterday we had started doing it. So some more knowledge in theoretical domain is required, and we will do that initially, and then we'll go for what is called as a MATLAB based simulation. So immediately you don't need to open up the MATLAB based simulation. So this was a circuit, it was shown yesterday. I think my screen is visible. So RLC circuit, everything has to be converted into Laplace domain. So L becomes Ls, C becomes 1 by Cs. Input is given to the RLC circuit and output is taken across Cs. If you take the output across Ls, the responses and everything will be different. But generally, we are taking the output across capacitor. That's why this is the output port VO, and input can be given anywhere in this series circuit. So all these 4 components are in series. Vin is nothing but a unit step input. You call it DC input, but I call it unit step because at t is equal to 0, I am applying voltage of 1. Now, don't think that it's 1 volt, it's one state or one step we are giving. So now that step, if it is 1 volt, it is called as unit step. Okay, somebody can give 20 volt also. You are going to get the shape of the waveform same, only the size will increase. So here, if you are giving 1 volt, the output voltage will start from 0 because you are considering it's an initially relaxed system. So initially the voltage across capacitor is 0. So voltage will start building up from 0. Not necessary if a capacitor has initially 4 volt or initially minus 3 volt, it will start from that. And final value of the capacitor voltage will be 20 volt. If you are inputting V in as 20 volt, final value of the capacitor will be 20 volt, but after certain time. Now, whenever you are finding a steady state error, first you have to see that you have taken enough time so that the output reaches steady state. You cannot measure steady state error when the waveform is at transient. So initially we found that waveform is doing some kind of oscillation and all. There you cannot find what is the output response. So you have to stretch the time axis while plotting it, and you have to find that output is at steady state. Steady state means the output is not showing any kind of variation or undulation. So first you have to let the output stabilize at a certain level. Then you are supposed to find out the difference between input and output. Then you will be able to comment what is the steady state error. So we'll find all that. Let us find out first transfer function and find out its step response. So while finding out step response, first I have to find out what is VO by VI. So in this case, VO by VI is nothing but the ratio of the impedances, because same current is flowing through all the components. So output voltage is proportional to output impedance, that is 1 by CS, and input voltage is nothing but proportional to addition of all these 3 voltages, that is R plus LS plus 1 by CS. So directly in one line you can write this down. So all these intermediate lines are not required because you are now growing in the domain of control system. So directly you can say that output by input is nothing but the ratio of impedances. So this is 1 by Cs, that is the output, and input is R plus Ls plus 1 by Cs. If you rationalize it, that means first you have to do the cross multiplication. It will become like this: 1 by LCS square plus RCS plus 1. We find it's a second order system because there are two energy storing element in this, so it's a second order system. Then I told you that whatever is the highest power of S, this is called as the order of the system, that you have to make equal to highest coefficient of 1. Not power you make 1, the coefficient of highest power term you make as 1. That means numerator and denominator has to be divided by LC. So it becomes A square plus R by L plus 1 by LC, and this is 1 by LC. Very important equation as far as second order system is concerned. This is for LRC system. Now the same thing if you do for MBK system. So generally it is MS square plus BS plus K. For MBK system also you can find out the same thing, and you can correlate MBK system transfer function with RLC system transfer function. But what will be the difference in that? Difference you have to find out. You are taking output across what? So we are taking output across M or B or K, because MBK all the things are in parallel. Anyways, so this is the RLC system second order system transfer function. Now this is very important thing I told you last day, that is this is the standard second order system transfer function. So let the system be anything: mechanical, electrical, hydraulic, pneumatic. For any second order system transfer function, this is the generalized, so this is the word you have to remember, this is the generalized second order system transfer function, which is actually showing three parameters, but S is actually the system variable. That is, we are defining everything in Laplace domain, that's why S has come. It is not a system parameter. So system parameter is omega n and zeta. So what is omega n? We can find out by comparing this transfer function with this transfer function. So you're finding here S square S square, you're finding R by L, this is 2 zeta omega n S. That means R by L is equal to 2 zeta omega n. And finally you are finding 1 by LC. Okay, you're finding 1 by LC is equal to omega n square. That means omega n is equal to 1 by root LC. So you have to compare these two. So what you are finding, omega n is equal to 1 by root LC. And numerator also you are finding the same thing, that is omega n is equal to 1 by root LC. So omega n, n stands for natural. The example is what is meant by natural frequency. So when there is no input, so we don't call it input in case of control system, we call it forcing function. Suppose you students are there, I tell you too much, do this, do that, do this, do that. So in that case, you are going to lose your original response. Okay. So when the teacher is not in the class, the way you behave, that is called as a natural response. You shout, you enjoy, and these and that. So that is your natural response. Okay. So whenever there is no input given to the system, how the system behaves, what kind of oscillation it produces, what kind of output it produces, that is called as natural response. What is called as forcing function, whenever some input is given. Suppose if I am giving step input, response of the system will be different. So all this depends on this RS. So CS by RS, I do. CS is the output, RS is the input. So then what I do is CS is equal to RS into omega n square plus this. So RS, if we put step, CS is going to be something. RS, if we put ramp, CS is going to be something. RS, if we put sinusoidal, CS is going to be something. So RS is the forcing function, or it is called as the input or excitation. So depending on RS, CS changes. If I am not putting any kind of RS to the system, whatever response we get, that is called as natural response. So any system is having a natural frequency, any system is having a natural response, and it's having forced response. What is meant by forced response? Here, if you are finding CS for RS as ramp, what is that CT called as a forced response? That is called ramp response. If you are finding CS for RS is equal to 1 by S, that is step response. In that case, CT will be called as a step response. So in that case, we are finding there is another type of frequency. Okay, not natural frequency. That frequency will be less than natural frequency. We call that frequency as omega D. That is called as damped response. Omega D is equal to omega n root under of 1 minus zeta square. So these are two different types of frequencies we find in case of second order system. One is called as natural response, omega n, that is 1 by root LC. Fn is equal to 1 by 2 pi root LC, because omega n is equal to 2 pi Fn. Unit of omega n is radian per second. So Fn is equal to 1 by 2 pi root LC likewise, and unit is hertz. So first thing we are supposed to find out what is the Fn, that is the natural frequency for any system. That is the first very important parameter in case of second order system. Second very important parameter, which is the main man for today's lab session, that is we are going to change the value of zeta, and we are going to get different systems. So you are changing zeta means you have to change the RLC value. So whenever you are changing the RLC value, the system is not same. So what we are going to do today is we are going to find 4 different values of zeta. So how to find zeta? This kind of numerical will be asked in the exam, that I will give you a transfer function in this form, and I'll ask you find what is the value of omega n and what is the value of zeta. So whatever is the constant here, suppose constant is 4. In that case, you have to write omega n is equal to omega n square is equal to 4. Omega n is equal to root of 4, that is equal to 2 radian per second. So this kind of transfer function will be given to you, or RLC value will be given to you, and depending on that you are first supposed to find what is omega n, what is zeta, and then you have to comment on zeta. So if zeta is equal to 0, so how to find zeta? Zeta means this r by l you have to compare with 2 zeta omega n, and omega n you know from the previous formula, that is omega n is equal to 1 by root LC. So 2 zeta divided by root LC is equal to r by l. From there find zeta in terms of R, L and C, and there's a golden formula you have to remember. Zeta is equal to R by 2 root under of C by L. C is in farad, L is in Henry, and zeta is not having any unit. That is the first thing you have to remember. Zeta does not have any unit. Okay, zeta is unitless. It's just a ratio. It's a ratio of resistor by 2 root under of capacitor divided by inductor. Now what is zeta actually? Zeta is called as damping factor. Damping ratio is called as. So what is damping ratio? Damping ratio decides whether the system is going to act very fast or system is going to act very slow. Whenever pataka is there, pataka mein damp lag jata hai. Okay, and pataka does not give a blasting sound. It dup karke sound deta hai and pataka blast is over. We are not happy with that. So in that case, what we say is zeta value is very high. If zeta value is very high, damping is very high. Damp ho gaya. Damping means it does not give more gain. Okay, so zeta value is very high means system is damped. In that case, whenever the system is damped, its output is less, its gain is less. Okay, so one very important thing we have to remember, that is zeta and damping, or zeta or damping and gain, they are inversely proportional. So ye bhi likh ke rakho, zeta and gain, they are inversely proportional. And we have seen the 3 golden rules. What is that? Gain is directly proportional to energy. That is the first thing. Gain is inversely proportional to stability, and energy is inversely proportional to stability. So these 3 golden rules we had. With that, I will add some 2-3 more rules with zeta. So first we understood that gain is inversely proportional to stability. That was the first thing. Energy is inversely proportional to stability. That is, more is the energy in the system, less will be the stability. And third thing, gain is directly proportional to energy. So gain and energy, they are directly proportional. Gain and stability, they are inversely proportional. Energy and stability, they are inversely proportional. And in this case, from the damping ratio, that is R by 2 root under of C by L. For MBK system, this formula will be a little different. So for MBK system, what will be the formula? Zeta is equal to, instead of R, we have to write B. FV system. Okay. In case of R, we have to write B. So zeta for MBK system is B by 2 root under of 1 by LC. Because in that case, it will be root under of root under of LC nahi, it will be L divided by root under of 1 upon, so this will be B by 2. So in case of MBK system, zeta will be B by 2 because R is substituted with beta, divided by root under of 1 upon MK, because C is 1 upon K. Okay. So in that case, zeta will be B by 2, likh ke rakho. For MBK system, zeta will be B by 2 root under of 1 upon M into K. So denominator, there will come 2 terms, M into K. Numerator will be 1 root under of 1 upon MK. That is inside the root under, and outside it will be B by 2. So you change the value of MBK and you will be finding different values of zeta. And 3 golden rules I told you: gain and energy directly proportional, gain and stability inversely proportional, energy and stability inversely proportional. Here we are adding the 4th rule. What is that? Zeta is directly proportional to stability. So more is the value of zeta, more is the overdamped region you are going, more is the value of zeta, more will be the stability. So please write it as equation number 4 in that golden rule of control system. More is the zeta, more is the stability. And more is the zeta, less will be oscillation. So that is another thing. So uh, output oscillation will reduce if you are increasing the value of zeta. We will see here today that if you are keeping zeta is equal to 0, so there are four cases. First case will be undamped. Okay, so every system, so now this is the value of zeta, how to find it. RLC value if I give, you can calculate zeta. Now let us find out what is the response. So every system opposes oscillatory response. Opposition to oscillator is called as damping. So this is the formal definition of zeta or damping. It is called as damping ratio. There is something called as damping ratio. There is something called as damping factor. All those things you can just find out what is the difference between damping ratio and damping factor. You can find out in book. You can Google. You will find out. But zeta, you have to understand what is zeta. Zeta is R by 2 root under of C by L. That's all. And you have to remember, more is the value of zeta, high will be the stability. So if I want a higher stability system, what you have to say is RLC system, R bada do. Okay, increase the value of R, increase the value of C. In that case, the value of zeta will be more. In that case, the stability of the system will be more. Okay, what is meant by stability? Output should not be uh, increasing in the time domain. Output should always asymptotically, it will become stable. It should go down very slowly. It should come to zero. So output should be converging. Output should be converging means over time the steady state value of the output should go to zero. Okay, that is what we want. So in this case, we will see what is the kind of output for different values of zeta. So every system opposes oscillatory response because oscillatory response is kind of a unstable response. So more is the energy in the system, oscillation occurs. Vehicle at 60 km per hour and vehicle at 160 km per hour. In that case, whenever the vehicle is at 60 km per hour, less energy is there. Oscillator or accelerator हम लोग थोड़ा सा press करते हैं 60 km per hour. Energy given to the system is less. Same system when we take it to 160 km per hour, in that case, vehicles start vibrating. Okay, because in that case we are inputting more energy to the system. That means we are inputting more energy means we are actually creating the instability in the system. Okay, so more energy given to the system, system starts oscillating. So whenever there is an oscillation in the system, suppose zeta is zero. Zeta is zero. We will prove it shortly. We'll prove it shortly that whenever you are finding zeta is equal to zero, and one more thing I told you last day while teaching the signal flow graph, and after that pole zero, we had shown that K value, that is the gain. So we have done one session, that is lecture number 22. There we have seen what is meant by system gain and what is meant by DC gain. Okay, so system gain is K. System gain is something which actually decides what is going to be the pole position. So system gain K is very less. In that case, poles are too much deep into J omega axis. Then we have started increasing the value of K, and in that case, we are finding that poles are shifting towards the right side. So more is the value of K, system poles will shift to the rightward side of the J omega axis. And that means poles have started becoming unstable. Then for a certain value of K, what we find is poles are exactly on J omega axis. So whenever poles are exactly on J omega axis means we are going to get a sinusoidal oscillation that is called as a sustained oscillation. So I have given you that experiment number 4. I think I have given plus minus 2j or something, and I have asked you to find out what is the response in time domain for that pole plus minus 2j, which is on j omega axis. So if it is plus minus 2j, you will be finding that output is a sinusoidal oscillation. So here the same thing, when zeta is equal to 0, I will prove it. You will be finding that the pole of the system is on j omega axis. So there are two poles for second order system. There are two poles. When zeta is equal to 0, that means r is equal to 0. You will be finding there are only two poles, and the two poles are coming on j omega axis. That means system is going to show oscillatory behavior, and that oscillator is neither uh, dying down nor it is expanding. Okay, so what we will find is the oscillation is a sustained oscillation. 2 radian per second might be its frequency. So zeta is equal to 0. This is called as a no damping. So how can you make zeta is equal to 0? So here it is r by 2 root under of c by l. Either you make resistance is equal to 0 or you make capacitance is equal to 0. Anything you make it, you are going to get a oscillation from the circuit. So zeta is equal to 0 means this is called undamped. Okay, this is called no damping or undamped case. In that case, circuit oscillates at free will. What is meant by that free will? That is actually frequency omega n. For every system, there is a omega n. For every system, there is a natural frequency. Okay, this is not a forced response. So a child when he is growing up, we everybody keep on telling him aisa karo, ye karo, wo karo. So that is the forcing function or that is the guiding function. If you don't do that, the student will grow up in his free will. So if he is really a painter or a singer by birth, then that talent will come out. Okay. Or if somebody, we always try to teach him control system or we try to teach him electronics, so he might become an engineer. There is a forced response, but in that case, that real true response of a painter or a singer, it will die down. So whenever we are connecting some kind of external forcing function, we don't get to see the omega n of the system. If we want to see the omega n of the system, in that case, we have to generate that oscillation first. So what is the oscillation? What is the natural frequency of the system? Just keep r is equal to 0. Then the system is different actually. It's a LC system. And you will be studying LC oscillator. Okay, so there are different types of oscillators. Crystal oscillator is there in every of the system. So that there is a crystal, piezoelectric crystal, it oscillates, it generates some kind of frequency. But initial days there was no crystal oscillator, there was only LC type of oscillator. So inductor and capacitor, when they're in parallel, there is no resistance. So RLC circuit, there is no resistance. Inductor and capacitor are there. Together they produce something called as a circuit, which is called as a tank circuit. Okay, and tank circuit actually produces some kind of oscillation. So that is actually giving us free will oscillation or called as omega n. So this is the initial case. Zeta is equal to 0 is called as no damping condition or undamped condition. So whatever code we have, in that code we can change the value of R, L and C. So तुमको 4 graph निकालना है, that's all. And you have to explain all those 4 graphs. Among them, zeta is equal to 0 graph is very easy. As soon as you are putting R is equal to 0, L or C का value कुछ भी रखो, 1 1 रखो. So in that case your omega n will be 1 by 2 pi root 1. That means 1 by 2 pi. That means 1 by 6 point something, 6.28. So you are going to get 0.16 radian per second around. That is called as oscillation frequency. So that response we have to see, and it's a sustained oscillation. When zeta is equal to 0, it's a sustained oscillation. It is neither going to increase nor going to decrease. So it is neither stable nor unstable, critically stable. Poles are on j omega axis. So 3 things are important. First, we have to select the value of R, L and C, and we have to create how much is the damping. That's the first thing. Second, with respect to the damping, what is going to be the pole position? Okay, what is going to be the pole position? So all these things I will show you with the proof just now. So first is select the value of RL and C in such a way that you are getting a typical value of damping. Second is whatever is the value of damping, depending on that, what is the pole position. And when we know the pole position, we know if this is a type of pole position, what is its step response in time domain. So if there are 2 poles, suppose -2 plus -3j, we have seen in the previous lab, that is if it is in the left hand side and there is a complex conjugate pole, what kind of response it is going to create? It is going to create a damped oscillation, and that oscillation is going to die down. So -2 plus -3j. So okay, so create zeta in such a way that the poles are -2 plus -3j. So you will be finding that zeta in that case is in between 0 and 1. Okay, so second case, actually this is the third case, and there is a little mistake here. It should be written 0 less than zeta less than 1. Okay, zeta greater than 0 and less than 1. This is the condition. So first case is zeta is equal to 0. We are going to get natural frequency. Second case is zeta in between 0 and 1. So though I have written it in the third case, but make it second. So zeta in between 0 and 1. In that case, suppose zeta is 0.15. So set RLC in such a way that you are getting zeta is equal to 0.15 or 0.3, somewhat like that. This is called underdamped. Okay, as long as zeta is less than 1 or greater than 0, zeta cannot be negative. Huh? So two are characteristic of zeta we have to remember. First is zeta cannot be negative. Zeta always is a positive thing, because if you see the ratio, it is r by l r by 2 root under of c by l. So r by 2 root under of c by l means it cannot be negative, because c, l, r, all these values cannot be negative. Okay, so zeta cannot be negative, that is the first thing. And second is zeta can be 0, zeta can be very high value, 10, 15, 30, it is there. And zeta is in a ratio form, zeta does not have a unit. So these are 2 characteristics we have to remember. So first zeta is equal to 0. In that case we get oscillation, sinusoidal oscillation. Ye yaad rakho, because I will show you all these outputs, and later on you have to do this simulation and you have to find out the response. Second is zeta can be in between 0 and 1. So change the value of r. Suppose keep r as suppose 0.3 and C and L is equal to 1. Okay, so keep r as 0.3 ohm and C and L is equal to 1 something. In that case, you will be finding zeta is equal to 0.15. So this is the second system. So first system zeta was 0, resistance was 0. Second system zeta is 0.15, underdamped system. Third case zeta is equal to 1. Okay, so for underdamped system, you'll be finding that system is behaving like it is generating e raised to minus 80 sine bt output. So we will see what is the output equation CT. That is the step response. We are giving step input every time, and we are designing four different systems, and we are finding what is the output for each system. So zeta is equal to 0.15. In that case, we'll be finding that poles are in the left hand side, and it's a complex conjugate pole. Left hand side and real pole, no. In that case, zeta is not in between 0 and 1. Okay, so left hand side and complex conjugate, that is minus 2 plus 3j, minus 2 minus 3j, those kind of thing. So depending on the value of zeta, depending on the value of k, you will be finding the pole positions. Once we know the pole position, we know how to represent its step response in time domain. Okay, so zeta is less than 1. What we find is, write down, it's called as a damped oscillation. That means sinusoidal but reducing damped or decreasing damped sinusoidal. Decreasing damped sinusoidal response we get for zeta in between 0 and 1. Third thing, zeta is equal to 1. Zeta is equal to 1 means you keep r is equal to 2 ohm, L is equal to C is equal to 1. So in the previous thing, formula of zeta, so keep r is equal to 2 ohm, so 2 by 2 is equal to 1. And C is equal to L is equal to 1. That means 1 farad, 1 Henry and 2 ohm. If this is the system, in that case you will find zeta is equal to 1. What is that thing called? Critical damping. Critical damping you will find waveform will start like this, charging. Output we are taking across capacitor, so it will start charging like this and very fast it will go up and stabilize. So this is the standard response, but very fast it will go, okay, like this and stabilize to 1 volt. And when it stabilizes to the final value, then you are supposed to find out what is the difference between input and output. So you people are confusing too much about steady state error. First thing you have to see output, and you should know how much is the input. So if I say steady state error, first you should ask what is the input. So input is the unit step. That means input is 1. And then steady state of the output. So when the output is changing, so output is increasing. Whenever it is increasing the linear graph, there you don't find the steady state error. You find steady state error after the output stabilizes. Okay, so after the output stabilizes, you have to see. So only initial 3 seconds, if you are checking output is increasing and you are finding steady state error, that is wrong. So first you have to let the output get stabilized. So maybe whenever you are plotting it, suppose I have asked that steady state error, whenever you are plotting it, maybe you have plotted for first 5 seconds and you are finding that it's still oscillating. So don't find steady state error in that case. So stretch that time axis, to maybe 15, 20, 30 or something. And you have found that after oscillation, output is stabilized to a certain value, whichever value it is. So for input 1 given, suppose it stabilizes to a value of 0.3 volt. So you have to find that stable zone and you have to find what is the output stable value. Whenever it is getting stable at 0.3 volt after oscillation, then you are supposed to subtract that output 0.3 from the input 1. So input is 1 volt, output is stable value is 0.3 volt. Output may oscillate initially. Initially it might go to 0.7, then come to 0.1, then again go to 0.6, then 0.15 likewise, and after a certain time it has stabilized to 0.3. So 0.3 is its stable value, and then 1 minus 0.3, that is 0.7 volt, is the steady state error. We will discuss about steady state error in this chapter only towards end. So for this every response also we can find out steady state error, and system is best if steady state error is equal to 0. That means output reaches to the input. So first case zeta is equal to 0, second case zeta is in between 0 to 1. So this third line a little correction is required. Here I should write 0 less than zeta less than 1. So that is the second case called as underdamping. Third case zeta is equal to 1. This is called as critical damping, best case. In critical damping there will be no oscillation. So out of these 4 responses, oscillation you will find for zeta is equal to 0. That is a undamped oscillation, natural response. Sustained oscillation, top peak, bottom peak, they are same. Second case, zeta in between 0 to 1, you will find that oscillation is there, but oscillation is reducing. That is, output is converging because it's a stable system. Zeta is in between 0 to 1 is also a stable system. Poles are there in the left hand side of S plane. Third case, zeta is equal to 1. In this case, you are finding the both the poles are on j omega axis. So this is a kind of a stable, is going towards stability. So both the poles are on the same position and on the real axis in the left hand side. This is also stable system. This is zeta is equal to 1, critically damping. But in this case, output is rising quite fast. And fourth case is zeta greater than 1. Whatever I have given in second, this is the fourth case. So keep R value very high. Keep R value very high. So make zeta is equal to 2, 3, 4 likewise. In that case also you will be finding that output is increasing like this. So I will just show you the difference between critical damping. So this is the for zeta is equal zeta greater than 1. Okay, this is the zeta greater than 1 response. Don't look at the what is the equation I have written. Don't follow the equation. Just see the shape. Okay, so this is zeta greater than 1. Okay, and zeta suppose is equal to 2. This kind of response you are finding. Suppose zeta is equal to 10. It will be further slow. Okay, further slow means after quite a lot of time it will reach to the input value. So here you are finding output is reaching to the input. That means steady state error has become 0. So you don't calculate steady state error here because there is a transient part. Output is still changing. As long as the output is changing, you don't calculate steady state error. Let the output get stable first, and then you find steady state error. So this is for zeta greater than 1, and this is for zeta is equal to 1. So zeta is equal to 1 means this is called as critical damping. So output is changing very fast, and very fast it is going and touching the final output as 1. So this is critical damping, or it can be further closer to the time axis. So it might go very fast like this, rise and touch the final output like this. And more is the value of zeta, flatter will be the response. So this is very sharp response. Sharp and flat, they are opposite. So this is a sharper response, that means fast rise time, very fast output is rising and touching the input. This is a little flatter. Maybe this is zeta is equal to 2. Zeta is equal to 10 means और नीचे से जाएगा output, और नीचे से. So after quite a lot of time it will touch the output. So this is for greater zeta, and this is for zeta is equal to 1. Okay. And we are going to generate all these waveforms. So we will see what it is. So zeta is equal to 0. System oscillates with natural frequency, and zeta is in between 0 to 1. Zeta system oscillates with damped frequency. So you must keep pen and paper and you must write down all these things. Anyway, I will be posting these notes to you. So zeta is equal to 0. System operates with natural frequency omega n. Now whenever system is in between 0 to 1, that means zeta is in between 0 to 1, at that time also there is an oscillation, and that oscillation is not same as omega n. That oscillation is in between, omega n is little less. So in that oscillation, that is a damped oscillation, zeta in between 0 to 1, that is called as under damped system. In that case, damped oscillation, that frequency, how much is that? Omega d is equal to omega n into root under of 1 minus zeta square. Suppose zeta is equal to 0.2. Zeta is equal to 0.2. In that case, this is 0.2 means 0.04. Zeta square is 0.04. So root under of 1 minus 0.04. That means root under of 0.96. Okay, so 0.96 means it will be omega d almost will be 0.98 omega n. But whatever it is, zeta cannot be negative. That is the first thing. And zeta in this case is in between 0 to 1. That means zeta, let's say 0.2. So this is zeta square is 0.04. 1 minus 0.04 is root under of 0.96. Root under of 0.96 can be around 0.98 or 0.99. So what you are finding is damped oscillation is almost equal to natural oscillation, but little less than natural oscillation, as long as zeta is in between 0 to 1. So omega d is called as a oscillation damping frequency or damped natural frequency. Omega n is value is highest, that is 1 by root LC, and omega d is omega n into root under of 1 minus zeta square, as long as zeta is in between 0 to 1. If zeta becomes 1, so that is the question. If zeta becomes 1, what is the value of omega d? It will be 0. Okay, substitute zeta is equal to 1. That means you want to find out how much is the damped oscillation when damping becomes equal to 1. So if you just substitute zeta here is equal to 1, you will be finding omega d is equal to 0. That means whenever there is critical damping and onward, that means higher damping, there is no oscillation in the system. So you can write down oscillation occurs, number 1, natural oscillation when zeta is equal to 0. Number 2, damped oscillation. What is damped oscillation? Little less oscillation frequency than omega n. So it can be 0.9 omega n, it can be 0.8 omega n, that is called as omega d. So little less oscillation when the zeta value is in between 0 to 1. So more is the value of the zeta, less is the oscillation in the system, less is the instability in the system. So this is another thing you have to correlate. As zeta value increases, oscillation in the system reduces. Oscillation means instability. That you have to understand. Oscillation means instability. More is the energy. Okay, कश्मकश चालू है. So more is the value of zeta, less will be the that is the frequency in the system, and at zeta is equal to 1, omega d becomes 0. If you substitute here zeta is equal to 1, omega d is 0, that means whenever there is a critical damping, there is no oscillation found in the system. And somebody says over damping, so omega d is equal to omega and root under of 1 minus, suppose zeta is equal to 3, which is over damping, zeta greater than 1, you are finding that omega d will become negative or imaginary. That means whenever zeta is equal to 1, omega d is 0, that is damped natural frequency is 0, and suppose zeta is 5 or 3 or 2, in that case omega d becomes imaginary. Omega d becomes imaginary means omega d रहता ही नहीं है. So for higher value of zeta, there is no oscillation, and for critical value of zeta, omega d is equal to 0, and for lower value of zeta, that is in between 0 to 1, yes, damped oscillation is there, omega d is equal to omega and root under of 1 minus zeta square, and for zeta is equal to 0, omega d is equal to omega n. You substitute here zeta is equal to 0, you are finding omega d is equal to omega n. That means system oscillates with natural frequency. Now all these four things we are going to see by analyzing the position of poles and its response. So you are doing experiment number 4. If I give you the position of poles, you can tell me what is its time domain step response. Same thing we are going to do here. So this is the second order system response. We know what is omega n. Omega n is 1 by root LC. We know what is zeta, r by 2 root under of c by l. So everything I say, if I say that I find what are the roots of this characteristic equation. So this is a closed loop transfer function Cs by Rs, and then characteristic equation is s square plus 2 zeta omega ns plus omega n square is equal to 0. Okay, so that z is equal to 0 I have not written, you have to understand. And from here you are finding the roots, and don't get scared, it is not at all difficult. So what is that? You are finding, you are solving this minus b plus minus root under of b square minus 4ac by 2a. If you do, you will be finding this is minus zeta omega n. Zeta into omega n, negative of that, because you are finding real parts are all negative. That means this roots are stable because real part is negative. Plus minus omega n root under of zeta square minus 1. Okay, so omega n root under of zeta square minus 1 is kind of omega d. Likewise, now you put here zeta is equal to 0. Whenever there is zeta is equal to 0, what you are finding, it will be plus minus omega n. Okay, so plus minus omega n, there are two poles, plus minus omega n, or this should be 1 minus zeta square, I think. So whenever so first let us see this case, fourth case here. Whenever zeta is equal to 0, you are finding it should be plus minus j omega n. So I think I have missed a j here. Okay, so yes, so this is like this. Is like this, omega n root under of 1 minus zeta square or minus j omega n. This equation and this equation, they are same. So actually this is the equation, roots minus zeta omega n plus minus j omega n root under of 1 minus zeta square. You write this equation, so roots of the equation like this, or you can take minus common from here, that minus root under of minus becomes j. So that j I have taken output side. So this is omega n into root under of 1 minus zeta square. So either you can write this, these are the two poles of second order system, or you can write this. So both are correct. Both are correct. There is nothing wrong in this. So again, I'll tell you the system. So this is the standard second order transfer function. This is the characteristic equation that equal to 0. You are finding roots are minus zeta omega n plus minus omega n root under of zeta square minus 1. Take minus 1 from here. So this becomes root under of 1 minus zeta square, and that minus root becomes j. So these are the two poles. Now in the first case, substitute zeta is equal to 0. Substitute zeta is equal to 0. That means this first term will go. That means first term goes means there is no real part. There is no real part means poles are on j omega axis. So if you are putting j is equal to 0, you will be finding the roots are on plus minus j omega n. What is plus minus j omega n? See that very beautifully it is shown here. See that these are two poles, plus minus j omega. Okay, because in this case there is no real part. The negative real part, positive, whatever it is, there is no real part, and it all comes from this formula. So there you should not get scared or anything. So first, this is the characteristic equation, this is the roots, take minus 1 common, this is the pole equation for the second order case. Now keep on doing the cases. If you are doing the cases, first case is zeta is equal to 0. In that case, you will be finding both the roots are coming on j omega axis. And I have given you this pole position, that is, I have given you, I think, plus minus 2j. If it is plus minus 2j for this fourth case, you are finding that all these four things I have shown together, see that this is the response. Okay, so zeta is equal to 0, s is equal to 1, 2 plus minus j omega n. So this will be showing you some kind of oscillation. I think amplitude thing is not shown properly or whatever, but there will be oscillation. And what will be the oscillating frequency? Oscillating frequency will be omega n. So see that this is the fourth case, zeta is equal to 0. So this is a very good question. I used to ask that in IA or something, that position of poles, in all these four cases, zeta is equal to 0, zeta is in between 0 to 1, zeta is equal to 1, and zeta is greater than 1. I have shown you what is zeta is greater than 1. So this is an overdamped case, zeta is equal to 1. This is also a case where there is no oscillation, because in this formula, if you are substituting zeta is equal to 1, we will find that only the real part will be remaining. So second case we will do later. Here substitute zeta is equal to 1. If you are substituting zeta is equal to 1, this whole imaginary part goes off. Okay, whole imaginary part goes off. In that case, we will be finding both the poles are at minus omega n. Okay, s12 zeta is equal to 1. Both the poles are s12 is equal to minus omega n. So what you will find is, what you will finding, there are two poles. Okay, there are two poles and they both are at minus omega n. Okay, and minus omega n is not a frequency, minus omega n is the amplitude. Okay, so in that case, you'll be finding both the poles are at the same position, and that will be kind of generating this kind of a response, that is called as a critically damped response. And if you are putting zeta greater than 1, if you are putting zeta greater than 1, in that case you will be finding that response is further slow. So in that case, zeta greater than 1. So if you are putting zeta greater than 1, suppose 2, zeta is equal to 2. In this case, it will be root under of 3 omega n. That means everything is real in that case. So if everything is real in that case, you will be finding that what is the pole position? Pole position is this. Okay, so this is the pole position when everything is real, and I think critical damping is shown above. So this is the under damping. This is called as critical damping. Okay, so this is the critical damping. So there are two poles at the same position in the real part. So this is also stable pole. So both the poles are at minus omega n. And if it is zeta is greater than 1, so if zeta is greater than 1, what you will be finding is there are two positions, both are real, but one will be minus zeta omega n plus this, another will be minus zeta omega n minus this. So for zeta greater than 1, you will be finding that there are two positions of real pole, but they are different position. And for zeta is equal to 1, you will be finding there are two poles on the real axis and they both are on the same plane. Okay, so likewise this below three diagrams is very important. Zeta is equal to 1, s12 both are minus zeta omega n. So there are both poles, zeta is equal to 1, both poles are at minus omega n. What is the response of that? Response of that you can plot. So you can take both the poles at minus 2 and plot their step response. You will be finding like this. This is called as critically damped response. That means very fast rising and touching the steady state, and steady state error is 0 or something. The same thing when you are changing the value of zeta a little bit, you are keeping the zeta value as 3, 4, 5 over damping condition. In that case, you will be finding S12, they are different. S12, if they are different, you are going to find the poles are like this at this minus 3, minus 2, suppose minus 5, minus 3. And what is the response for that? Response will be some same thing, but it will be rising very slow. Okay. So both poles at the same position, it is critical damping, rising very fast and touching the output. Both poles on the real axis, but different position, it will be very slow rising likewise. But most important for our lab is this case, that is zeta is less than 1. So in this equation, whatever equation you're finding here, in this equation, substitute zeta is equal to suppose 0.2. So decide r by 2 root under of c by l in such a way that zeta is equal to, let's say, 0.2. In that case, you'll be finding that if you substitute here, you'll be finding that poles are like this. So they're imaginary and they are in the left hand side of S plane. So what kind of response this creates? It will create this kind of thing. So this is a kind of a response which is called as oscillatory response, but this is converging. So after a certain time, so in this position, this part is called as transient time. So from initial up to this time, this is called as a transient time. You don't find steady state error in transient time. You first let the waveform to get stable, come at steady state. Okay, so the waveform has come at steady state here after this time. Now this is the output and this is the input, difference between that. Not necessary that steady state response will be same as the input, not necessary, it can be undulating and it can get steady state here. Okay, that is, let's say 0.6 volt. Now this is input is 1, so every time I have shown 1 is the input, because we are finding the step response of the system. So when the input is 1 and suppose this oscillation has come here, suppose 0.6, how much is the steady state error? So input is 1 and response is stabilized at 0.6 in a different system. So steady state error is 1 minus 0.6, that is 0.4 volt. Okay. So for steady state error, you have to first allow the system to come to steady state. For that, whatever plotting you are doing, you have to keep t value high. That means you have to plot the graph for a higher value of t. Then bring the waveform at steady state. Check what is the steady state value. If you have given input step 1 minus that steady state value, that is equal to the steady state error. Now if the input is ramp, not about this, if the input is ramp, in that case input is also increasing with respect to time, output is also increasing with respect to time. Output is never going to go at steady state. So in that case, after a certain time, maybe 5 seconds, 10 seconds or something, you have to mention that at this time I am finding how much is the error. So if the input is t means at 1 second output is 1 volt, 2 second output is 2 volt, 3 second output is 3 volt. In that case, after 10 seconds, okay, so system response will be, that is input will be 10 volt because input is t. Then find how much is the output. So the output is 8 volt after 10 seconds. So input is 10 after 10 seconds, output is 8 after 10 seconds. In that case, at 10 seconds, the output error is 10 minus 8, that is 2 volt. We will discuss all these things during we are doing steady state. So these are the 4 responses. Okay, so first response we are going to plot is this: zeta is equal to 0. So 4 different systems they are. It is not that same RLC circuit will produce all these 4 response. No, they are 4 different circuits. That means there are 4 different set of values of R and L and C. So first circuit we will see, maybe we will keep L is equal to 1, C is equal to 1, R is equal to 0, and we'll plot what is its step response. Input is always step input. Okay, so we are giving step input, there is no oscillation into that, but we are finding that it is producing some kind of oscillatory output. Okay, so this is the first kind of output we are going to observe, and depending on pole position we can change the frequency. Okay, so you keep different value of L and C, you will be finding this frequency of oscillation becomes different. That is something you are supposed to see. Second, we will check this waveform. Okay, so we will keep suppose RLC value in such a way that we will design that suppose zeta is equal to 0.2. Okay, so R will keep as 0.4, L is equal to C is equal to 1, we will keep. In that case, we are going to find that R by 2 root under of C by L, so C by L is 1, and R by 2 is 0.4 by 2 is 0.2. Okay, and generally for generating this kind of good waveform, you should keep the zeta value less than 0.2 or 0.3. If you are keeping zeta value 0.9, then also it is underdamped, no problem, technically you are correct, but itna sara oscillation nahi dikhega usme. If you want to see the oscillation, your R value should be closer to 0. That means when the zeta value is not R value, zeta value should be closer to 0. So whenever your zeta value is closer to 0, then only there is more instability. Then only you are going to see more oscillation in the system. So this is the second case. We will keep R value as 0.4. You can write down all these values. So first case, R is 0, C is 1, L is 1. Second value, suppose R we will keep as 0.4, C and L we will keep as 1. So in that case, zeta is equal to 0.2, and we will see what is the kind of a response we are getting. Third case, we will keep R is equal to 2. Okay, and C and L is equal to 1, 1 we will keep. So in that case, R is equal to 2, R by 2 means 2 by 2 is equal to 1, and C by L is 1, 1. So in that case, zeta is equal to 1. We will get this kind of response. Okay, and fourth case, overdamping. Suppose we want the zeta value to be 3, let's say. Okay, we want zeta value to be 3. So R value you keep as 6. Okay, so 6 by 2, that is 3. And C and L you keep as 1. So these are the 4 cases, these are the 4 responses we are supposed to find out. And there is nothing much to see in these 2 responses, that is overdamp, underdamp and critical damp. Sorry, overdamp, critical damp and undamped. And there is nothing much to see in this case. But yes, underdamped response we have to check 5 parameters. First thing is what is delay time, second thing what is rise time, third thing what is peak time, fourth thing what is settling time, and fifth is what is percentage overshoot. So first we will do this, that is undamped case, second we will do critical damped case, third we will do overdamped case, finally we will go into underdamped case. But while writing in the exam, you have to go on increasing with the effect of zeta. So in the exam while you are writing, first you have to do undamped, then you have to do underdamped, then you have to do critical damp, and then you have to do overdamped. So you have to go in the order of increasing value of zeta whenever you are writing the same question in the exam. So everything is coming from this equation. Everything is coming from this equation. That is s square plus 2 zeta omega ns plus omega n square s12. So just solve this and you will be finding the roots of equation is like this. Take minus 1 outside, so this becomes plus minus j omega root under of 1 minus zeta square. First case, substitute zeta is equal to 0. You will be finding if you are substituting zeta is equal to 0, s12 is plus minus j omega n. You have to say poles are on j omega axis, there is no real part, output is sustained oscillation. In the exam second case, you have to say that whenever zeta is in between 0 and 1, in that case what we are finding is what we'll be finding is that poles are in the left hand side. So you substitute here some value of zeta, let's say 0.2 or something. Okay, so both these terms will be there. That means minus 2 plus minus 3j it might come. So in that case, zeta is in between 0 and 1. You'll be finding that suppose zeta is equal to 0.2, substitute, you'll be finding there are both stable roots. Both stable roots, that means in the left hand side of j omega axis, but they're imaginary conjugate poles. What will give us the response like damped oscillation? That means we are going to get a decreasing kind of a sinusoidal, and initially there will be a transient part and then there will be steady state part, and these are the parameter values. So what is delay time, rise time, peak time, settling time, percentage, MP, all those things you have to find from the graph. Third case, in the same equation, third case, put zeta is equal to 1. In this case, if you're putting zeta is equal to 1, imaginary part goes off. Both the poles are minus omega n. That means both the poles are on real part of j omega axis, so real part of S plane. Both the poles are on the same position. So minus omega n, the other two poles, and we know what is the response, step response. So it is very fast rising, and after a certain time it will touch input axis. This is the third case. Fourth case, let us keep a very big value of zeta in this equation. So let's keep zeta is equal to 3. In that case, we'll be finding that both the poles will be on the j omega axis, on the real axis. That is, so in this case, if you put substitute zeta is equal to 3, you'll be finding both the poles are real and both the poles are negative. So in this case, we'll be finding that the roots that are there, that is actually equal to at s1 and s2, where s1 and s2 both are negative. And what is the response in that case? Very slowly moving up kind of a response. So this is the four things we are going to see. I'm giving you a break for 2-3 minutes. You just come back.